Welcome everybody. So now we are starting to, in these last couple weeks, we're gonna start to tie up the last few loose ends that we left throughout the course. So in this week, we're gonna finish all the proof, remember, of all the equivalents of the axiom of choice. Now that we have this tool of the ordinals. So the ordinals are gonna be a good tool to talk about many of the things that I've been talking but couldn't fully talk in detail. So we'll see this in the next couple of weeks. So the first theorem I want to show you is Hartog's theorem. Hartog's theorem is essentially saying that there are ordinals that are large. So for every set, what it says is that for every set A, so it doesn't matter what the size of this set A, so think of a big set A, there is an ordinal alpha that is not dominated by A. Okay, so just as a reminder, alpha dominated by A means that there is a one-to-one function from alpha to A, right? That's what it means to be dominated. Alpha being dominated by A, which we write with this symbol, this curly less than or equal, means that there is a one-to-one function from alpha to the set A. Okay, so here the theorem is saying there is an ordinal that is not dominated by this set. So there cannot be like a set that is so large that dominates all ordinals, essentially. So no set can dominate all ordinals. That's what Hartog is saying. It's going to be quite useful in the proofs coming up. So let's prove this. Actually, it's going to be a constructive proof. This proof is not going to use the axiom of choice because, well, we want to use it to prove the equivalent versions of the axiom of choice. So we don't want to use it. We use the axiom of choice here. If we were going to use the axiom of choice, we could say that this is dominated will be equivalent to saying there is an onto function from A into alpha. There are other equivalences, but let's stay with this one so that we don't use the axiom of choice. So consider the following. The set of all ordinals which are dominated by A. And, well, it says set, but it's obvious you're not using the subset axiom right there. I just put beta such that something. So we have to show this as a set before we can talk about it as a set, right? So why is this? Well, I claim the following. We claim there is a set because alpha is the set of epsilon images of the following set B, comma R, such that B is a subset of A, R is a subset of B cross B, R is a well-ordered. Okay, so I'm claiming that if you take the epsilon images of all the pairs B, comma R with the property that B is an actual subset of A. Okay, so here we are taking these guys. They belong to the power set of A cross power set of A times A, right? Because we are taking B, which is a subset of A, and R, which is a subset of B cross B, which is a subset of A times A. So we can use the subset axiom to define this set, and we are considering the pairs B, comma R, such that R is a well ordering of B. Okay, so it's a binary relation, so we're saying it's actually a well ordering. Some are well ordering, some are not. Just consider the set of the ones which are well ordered for B a subset of A. And we claim that this thing up here is exactly the set of epsilon images of these guys. Well, that's kind of clear, right? Because if you're an ordinal and you're dominated by A, that means you're there's a bijection between you and a subset of A, right? So if you have a one-to-one map from an ordinal beta to a set A, then the image of this set of this ordinal is a subset of A, right? And if we define R to be the set of all A, comma B that belong to B squared, such that F inverse of A belongs to F inverse of B. So here is A comma B, and here is F inverse of A, F inverse of B. We will get that this relation is exactly isomorphic two belongs, right? So belong here and are here will be an isomorphism. So we get that every ordinal that is dominated by A is isomorphic to one of this form for a subset of A. And if it's isomorphic and it's an ordinal, then that means that beta is an epsilon image of that well ordering. And the other way around is quite obvious, right? So if you have the epsilon image of something of this form, well, the epsilon image gives you a bijection between the ordinal and the well ordering. So if you have the epsilon image of this guy, if the epsilon image of something like this is beta, then beta, of course, you have a one-to-one function from beta to A, given that the epsilon by the epsilon image. Okay, so that's why this is the set, and then whatever you're using here, then use replacement. Okay, so use the replacement axiom right there, because now we have a set of images. The epsilon image is unique, right, given a well ordering. So that tells you that alpha is a set. Okay, so it's a set, so that means that took a while, but it's important to know that it's a set. And then also, what else do we have? We know that alpha is transitive. It's a transitive set, right? Because if gamma belongs to beta, which belongs to alpha, right? Then we have that gamma is a subset of beta, which is dominated by alpha. Sorry, by A, because that's what it means to belong to alpha, to be dominated by A. So we get that gamma is dominated by A2. So it must be also in alpha. Okay, so it's a transitive set of ordinals. So if you have a transitive set of ordinals, we proved last week that means you are an ordinal, right? Remember that every ordinal is a set of all the previous ordinals. So every ordinal is itself, not only is an ordinal, but it's also a set of ordinals, right? Every ordinal is a set of all the previous ordinals. So if you have a set of ordinals that is transitive, if you're restricting yourself to ordinals, to sets of ordinals, then being transitive means that you're closed downwards, right? That if exactly this thing up here means that if you close downwards, something belongs. If gamma is less than beta, and beta belongs to alpha, then so does gamma. So you're a downward close set of ordinals, so you have to be an ordinal too, essentially the next ordinal that is not in the set. No ordinal belongs to themselves, so an alpha does not belong to alpha. We hope we proved that last time. So that means that alpha is an ordinal and alpha is not dominated by A, because otherwise it would belong to alpha, right? Alpha is the set of the things that are dominated by A. So this one is not. Cool. So we have constructed an ordinal that is not dominated by A. Actually, we found we built the least ordinal not dominated by A. And this is going to be very useful in the next videos. See you guys later.